What if I told you time travel is not just science fiction, but something physics already allows? Not in the way movies show, but in a much stranger, real way. Scientists have recently shown that atoms can exist in two places at once and even move while being connected across space. So the question is, if reality itself works like this, can we actually travel through time? To answer that, we first need to understand something very basic. What is time? In everyday life, we think time is fixed. Seconds pass, minutes move forward, and everything flows in one direction. But physics tells a completely different story. Time is not absolute. It's not the same for everyone. It can stretch, slow down, and even behave differently depending on motion and gravity. So time is not just something we measure, it's something that can actually change. This idea comes from Einstein's theory of relativity. According to Einstein, the faster you move, the slower time passes for you. This is called time dilation. And this is not just theory, it has been experimentally observed. For example, atomic clocks placed on fast-moving airplanes tick slightly slower than clocks on Earth. Astronauts in space age just a tiny bit less than people on Earth. So, technically, time travel to the future is already possible and has been observed in small amounts. If you could travel close to the speed of light and come back, you would have moved into the future, not by magic, but because time itself slowed down for you. But things become even stranger when we go into the quantum world. At very small scales, particles don't behave like solid objects. They behave like waves. This leads to something called superposition, where a particle can exist in multiple places at the same time. Yes, literally. Not one place, but many. And then comes one of the strangest phenomena in physics: quantum entanglement. This is when two particles become connected in such a way that measuring one instantly determines the state of the other, even if they are separated by large distances. But importantly, this connection cannot be used to send information faster than light. It's like the universe is linking them together beyond space. For a long time, scientists only observed this in tiny particles like electrons. But recently, they pushed this idea much further. They performed experiments using large molecules containing up to 2,000 atoms. These molecules were sent through a special setup called an interferometer, and the result was shocking. They created interference patterns, which means these molecules were behaving like waves spread across space. In other words, even massive objects can exist in multiple positions at once. This confirms that quantum behavior is not limited to tiny particles. And then came an even more advanced experiment. Scientists cooled helium atoms to extremely low temperatures, close to absolute zero. Then, they made these atoms collide. This produced pairs of atoms moving in opposite directions. But here's the key point. These atoms were not independent. They were entangled in their motion. That means if one atom moves in a certain way, the other is instantly correlated with it. Scientists tested this using something called Bell's inequality, a method that distinguishes between classical and quantum behavior. And the results showed clear evidence that these correlations cannot be explained by normal physics. This is real quantum entanglement in massive particles and even in motion. So, what does all this mean? Does this allow us to travel through time? The answer is, not yet. Quantum entanglement does not allow faster-than-light communication. It does not let us send information into the past, and it does not teleport objects instantly. But these experiments reveal something much deeper. They show that reality itself is not as fixed as we once believed. Space and time may be more flexible than we understand. And one of the biggest challenges in physics today is this: to connect quantum mechanics with gravity and Einstein's theory of space-time. If we can solve that, we might discover entirely new ways to understand time itself. So, is time travel possible? To the future, yes, it already happens. To the past, we don't know yet. But experiments like these are pushing the boundaries of what's possible. And they remind us of one simple truth. The universe is not just stranger than we imagine, it is stranger than we can imagine.